You are correct. The laundry load is not required to be included in the general lighting load calculation for a dwelling unit as per the 2020 National Electrical Code. Section 220.52b requires a 1500-volt ampere load to be included in the general lighting load. Section 210.11c2 requires a laundry branch circuit as per Section 210.52f. Section 210.52f exception number 1 and 2 states that a laundry circuit is not required for a dwelling unit with a total floor area of 1000 square feet or 92.9 square meters or less. Since exception number 1 and 2 waives the requirement for a laundry circuit in certain dwellings, the corresponding lighting load associated with the laundry circuit is also not required to be included in the general lighting load calculation. Therefore, for dwellings that meet the criteria of exception number 1 and 2, the laundry load is not required to be used in the calculation of the minimum code required general lighting load. Let's break this down further to ensure a clear understanding of the National Electrical Code provisions and their implications on electrical load calculations for dwelling units, especially concerning laundry circuits. The National Electrical Code, or NEC, serves as a comprehensive set of standards and guidelines for safe electrical installations. It's crucial for electricians, contractors, and inspectors to adhere to these regulations to ensure the safety and proper functioning of electrical systems. Section 220 of the NEC deals with branch circuit, feeder, and service calculations. These calculations determine the minimum electrical capacity required to safely and effectively power a building or dwelling unit. Section 220.52 specifically addresses general lighting loads in dwelling units. It outlines the method for calculating the minimum lighting load that must be included in the overall electrical load calculation for the building. According to 220.52b, a 1500-volt ampere load must be included in the general lighting load. This requirement accounts for the electricity used by lighting fixtures throughout the dwelling unit. It's important to note that this is a minimum requirement, and the actual lighting load may be higher depending on the number and type of lighting fixtures installed. Section 210 of the NEC covers branch circuits, which are the circuits that supply power to outlets, lighting fixtures, and appliances. Section 210.11c2 specifically addresses laundry branch circuits in dwelling units. It mandates that a laundry branch circuit must be installed in dwelling units as per the requirements outlined in 210.52f. This ensures that there is a dedicated circuit available to power laundry appliances such as washing machines and dryers. Section 210.52f provides specific requirements for the installation of laundry branch circuits in dwelling units. It specifies the location of the required receptacle outlet and other details related to the circuit's installation. However, it also includes exceptions that waive the requirement for a laundry circuit in certain situations. Exception number 1 and 2 of 210.52f state that a laundry circuit is not required for a dwelling unit with a total floor area of 1000 square feet or 92.9 square meters or less. This exception recognizes that smaller dwelling units may not have the same need for a dedicated laundry circuit as larger homes. In these smaller dwellings, the electrical load associated with laundry appliances may be adequately supported by other general-purpose circuits. The key point is that since exception number 1 and 2 waives the requirement for a laundry circuit in certain dwellings, the corresponding lighting load associated with the laundry circuit is also not required to be included in the general lighting load calculation. This means that for dwellings that meet the criteria of exception number 1 and 2, the 1500-volt ampere load typically associated with a laundry circuit does not need to be added to the minimum general lighting load calculation as specified in 220.52b. Here is an example to illustrate how these code sections work together. Imagine a small apartment with a total floor area of 800 square feet. Because this apartment falls under the size limit specified in exception number 1 and 2 of 210.52f, a dedicated laundry circuit is not required. As a result, a 1500-volt ampere load associated with a laundry circuit does not need to be included in the general lighting load calculation for this apartment. In contrast, consider a larger house with a total floor area of 1500 square feet. In this case, exception number 1 and 2 of 210.52F do not apply, and a dedicated laundry circuit is required. Therefore, a 1500 volt ampere load associated with the laundry circuit must be included in the general lighting load calculation for this house. It's important to note that these calculations are intended to determine the minimum required electrical capacity. In some cases, it may be necessary to increase the capacity to accommodate the actual electrical loads of the dwelling unit. For instance, if a dwelling unit has a large number of lighting fixtures or power-hungry appliances, it may be necessary to increase the size of the service entrance and feeder conductors to ensure adequate power is available. In addition to the specific code sections discussed above, it's also important to consider other relevant requirements in the National Electrical Code when performing electrical load calculations. These may include requirements for appliance circuits, heating and air conditioning equipment, and other specialized loads. It's also important to consult with local electrical codes and regulations, as these may vary from the National Electrical Code in some jurisdictions. Furthermore, it's always advisable to consult with a qualified electrician or electrical engineer to ensure that electrical installations comply with all applicable codes and regulations. These professionals have the expertise and knowledge to perform accurate load calculations and design safe and reliable electrical systems. In summary, understanding the interplay between 220.52b, 210.11c2, and 210.52F is essential for accurately calculating electrical loads in dwelling units. By carefully considering the size of the dwelling unit and the requirements for laundry circuits, you can ensure that electrical installations comply with the National Electrical Code and provide adequate power for all electrical needs. Remember, accurate load calculations are crucial for ensuring the safety and reliability of electrical systems. By following the guidelines and regulations outlined in the National Electrical Code, you can help prevent electrical hazards and ensure that electrical systems function properly for years to come. Now let's delve deeper into some related concepts and considerations. Firstly, it's crucial to differentiate between the terms volt-amperes or volt-amps and watts. While both are units of electrical power, they represent different aspects. Watts measure real power, which is the power actually consumed by a load and converted into useful work, such as heat or light. Volt-amperes, on the other hand, measure apparent power, which is the total power supplied to a load, including both real power and reactive power. Reactive power is associated with energy stored in and released by inductive and capacitive components, such as motors and capacitors. In alternating current, or AC, circuits, real power and apparent power are not always equal. The ratio between real power and apparent power is called the power factor. A power factor of 1 indicates that all the apparent power is being converted into real power, while a power factor less than 1 indicates that some of the apparent power is being used to store energy and is not being converted into useful work. When calculating electrical loads, it's important to use volt-amperes as the unit of measurement, as this accounts for both real power and reactive power. This ensures that the electrical system is adequately sized to handle the total power demand of the load. Secondly, it's worth discussing the concept of demand factors. A demand factor is a ratio that represents the percentage of the total connected load that is expected to be in use at any given time. Demand factors are used to reduce the calculated load, as it's unlikely that all electrical loads in a building will be operating simultaneously at their maximum capacity. The National Electrical Code provides demand factors for various types of loads, such as lighting, appliances, and heating and air conditioning equipment. These demand factors are based on statistical data and engineering judgment. By applying demand factors to the connected load, you can obtain a more realistic estimate of the actual load that the electrical system will need to handle. However, it's important to use demand factors cautiously and to consider the specific characteristics of the building and its occupants. In some cases, it may be necessary to increase the calculated load to account for unusual or unpredictable load patterns. Thirdly, let's touch upon the topic of voltage drop. Voltage drop is the decrease in voltage that occurs along a conductor due to the conductor's resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code sets limits on the amount of voltage drop that is allowed in branch circuits and feeders. These limits are intended to ensure that equipment receives adequate voltage to operate properly. To minimize voltage drop, it's important to use conductors that are of adequate size and to keep the length of the conductors as short as possible. You can also use voltage drop calculators to estimate the voltage drop in a circuit and to select the appropriate conductor size. Fourthly, it's essential to consider the impact of harmonics on electrical systems. Harmonics are distortions of the sinusoidal waveform of alternating current. They are caused by nonlinear loads, such as electronic devices, variable frequency drives, and arc furnaces. Harmonics can cause a variety of problems, including overheating of equipment, increased energy losses, and interference with communication systems. To mitigate the effects of harmonics, it's important to use harmonic filters or to specify equipment that is designed to minimize harmonic generation. You can also perform harmonic studies to assess the level of harmonics in an electrical system and to identify potential problems. Fifthly, let's briefly discuss the importance of grounding and bonding. Grounding is the connection of an electrical system to the earth. It provides a path for fault current to flow back to the source, which helps to trip circuit breakers or fuses and prevent electrical shock hazards. Bonding is the connection of metal parts of an electrical system to each other. It creates a low impedance path for fault current to flow, which helps to minimize voltage differences and prevent electrical shock hazards. Proper grounding and bonding are essential for ensuring the safety of electrical systems. The National Electrical Code provides detailed requirements for grounding and bonding. Sixthly, it's crucial to understand the different types of overcurrent protection devices. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. They interrupt the flow of current when it exceeds a predetermined level, preventing damage to equipment and reducing the risk of fire. Circuit breakers are resettable devices that can be used repeatedly, while fuses are one-time devices that must be replaced after they have blown. The National Electrical Code specifies the type and size of overcurrent protection devices that must be used in various applications. Seventhly, let's touch upon the topic of surge protection. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges, such as those caused by lightning strikes or power line switching. SPD divert the surge current to ground, preventing it from damaging sensitive electronic equipment. The National Electrical Code recommends the use of SPD in various applications, particularly in areas that are prone to lightning strikes or power line disturbances. Eighthly, it's important to consider the impact of energy efficiency on electrical system design. Energy-efficient equipment and lighting can significantly reduce energy consumption and lower operating costs. The National Electrical Code provides requirements for energy-efficient lighting and equipment. You can also use energy modeling software to evaluate the energy performance of different electrical system designs. Ninthly, let's briefly discuss the importance of regular electrical system maintenance. Regular maintenance can help to identify and correct potential problems before they lead to equipment failures or safety hazards. Maintenance activities may include inspecting wiring, testing overcurrent protection devices, and cleaning equipment. The National Electrical Code recommends that electrical systems be inspected and maintained on a regular basis. Lastly, it's crucial to stay up to date on the latest changes to the National Electrical Code. The NEC is revised every 3 years, and it's important to be aware of the latest changes to ensure that electrical installations comply with the most current requirements. You can attend NEC training courses or subscribe to industry publications to stay informed about the latest changes. By understanding these related concepts and considerations, you can gain a deeper appreciation for the complexities of electrical system design and ensure that electrical installations are safe, reliable, and energy efficient.